Today I'll talk about the life cycle of a star. That is, how a star is born and what happens after a star collapses. You must have heard that a star collapses into a black hole, but this is not always true. We have to evaluate many things before we can find out about the life cycle of a star. And this video will also set up the base for the video series that I'm going to do on black holes. So make sure you stay tuned in case you are interested. All the stars are formed from something known as stellar nebulas. These are huge clouds of dust and gas floating around in the universe. Due to the gravity of the substances present in the nebula, everything spirals towards the center of the nebula over millions of years. If the gravity is strong enough, then all the material collapses to the center, which leads to the formation of a protostar. A protostar needs to get a temperature of 10 million degrees Celsius for fusion to occur. If the conditions at the protostar are suitable, then the hydrogen present in the core of the protostar starts fusing helium, which releases energy and the life of a star begins. If the mass is not large enough, then the protostar cannot give energy as nuclear fusion is not possible. If you want to learn more about nuclear fusion, then check out this video. The star keeps fusing lighter elements to heavier atoms, starting with hydrogen up to iron. But this process depends upon the mass of the star. For example, an average star like our Sun burns hydrogen into helium. When the hydrogen at the core is fused, the reaction starts taking place on the outside of the core. This also leads to the expansion of the size of the star. According to calculations, because of this reason, the Sun can grow up to the size where it can touch the Earth's orbit. In the next 5 billion years, it is possible that the Sun may evaporate Earth. This humongous phase of a star is called the red giant phase. After burning all the hydrogen into helium, the Sun will convert helium into heavier atoms like carbon, but not very efficiently as the mass of the Sun is not large enough. Eventually the fusion will stop and the force of gravity towards the center will get larger than the force produced by fusion, which counters it. This leads to the shrinking of the radius of a star. After this, the star shrinks and radiates whatever energy it has already generated. This phase is called white dwarf. The star starts cooling as there is no more fusion happening inside the core. Eventually the star will cool off into a black dwarf and remains there, floating in the universe forever, completely dark. This process was for stars which are about 1.4 times the mass of the Sun or less. This is also called the Chandrasekhar limit, as it was derived by an Indian astrophysicist, Subramanian Chandrasekhar. The Chandrasekhar limit is the maximum mass of a stable white dwarf star. The currently accepted value of Chandrasekhar limit is about 1.4 solar mass. White dwarfs resist gravitational collapse primarily through electron degeneracy pressure. That is because of Pauli's exclusion principle. Now, let us talk about the massive main sequence stars. They follow the same path up to the super red giant phase. They reach here faster than average stars because the reaction takes place at a faster rate because of more mass. The only difference is that due to their massive mass, the fusion process takes place up to iron. A super red giant contains all the elements up to iron. The fusion does not stop at carbon or helium. Iron cannot be fused into heavier atoms, so the nuclear fusion eventually stops, and the collapse of this huge amount of mass results into a supernova. These are the biggest and most powerful explosions ever observed by humans in the whole universe. A supernova is so bright that it can outshine all the other stars for several weeks. The core of the supernova has immense pressure and heat, which results in the formation of almost all the elements found in the universe, and these are ejected as stardust. So yes, it is right that we are all made up of stardust. After this, a neutron star is formed by the fusion of electrons, protons, and other subatomic particles at the center of a supernova. This happens if the core is about 1.4 to 2.8 times the mass of our Sun. Once formed, they no longer actively generate heat and cool over time. However, they may still evolve further. Neutron stars that can be observed are very hot and typically have a surface temperature of about 600,000 Kelvin. A neutron star is an extremely dense object. A single cubic centimeter of a neutron star weighs about 400 million tons. This is like a couple million trucks fitted inside 1 centimeter cube. The surface gravity on a neutron star is about 100 billion times that on Earth. Neutron stars are a result in many other interesting objects like pulsars and magnetars. There are thought to be around 1 billion neutron stars in the Milky Way. If the mass of the core of a neutron star is 2.8 times more than the Sun, then even the neutrons can't resist the force of gravity, and it further causes a gravitational collapse, which leads to the formation of black holes. The gravitational pull near a black hole is so powerful that nothing can escape it, not even if you're traveling at the speed of light. That is, of course, even light cannot escape from a black hole. Black holes are one of the most bizarre and interesting things in the whole universe. I'll talk more about black holes in the upcoming videos. So, this is all about stars, starting from stellar nebulas to white dwarfs, neutron stars, or in some cases, black holes. Hope you find this video informative, and thank you so much for watching it till the end.